Welcome to experiment number 5, and today we will create and simulate a half-wave rectifier circuit with RC load. The objectives of the experiments are: number 1, to simulate the half-wave rectifier with RC load using the Pspice software. Number 2, to utilize the software to observe the behavior of a half-wave rectifier with RC load. And number 3, to determine the various quantities using the Pspice software. To start, one of the common applications of rectifier circuit is to convert an AC voltage input to a DC voltage output. In this design circuit, the half-wave rectifier has a parallel RC load. The purpose of the capacitor is to reduce the variation in the output voltage, making it more like DC. So the resistance may represent an external load, and the capacitor may be a filter, which is part of the rectifier circuit. For this experiment, we will set the value of the resistor to 200 ohms, the capacitor to 100 microfarad, and we will use V sign as the source and D brick for the diode. The AC source should dissipate 220 VRMS at 60 Hz. In the simulation setting, we will choose time domain transient for the analysis time, and we will set our runtime time to 16.67 milliseconds or 60 Hz for one period of the source. We will also set our maximum step size to 10 microseconds to get an adequate sampling of the waveforms. Now let's go to OrCAD Pspice. So in the schematic, we have here a transient sine voltage source for our VAC, D-brick for our diode, capacitor, and resistor. For the V amplitude, we are given a 220 VRMS, multiply it to square root of 2, and we will get 311.127. That will be our input for the V amplitude. Frequency 60 Hz, AC 0, voltage offset 0. For the value of the capacitor, it's 100 microfarad. For the resistor, 200 ohms. Now let's connect the components. And we will connect ground, 0 cap sim, okay. Then use simulation profile. For the simulation settings, set our runtime time to 16.67 milliseconds. Maximum step size, 10 microseconds. Click apply, okay. For table number 1, we are to obtain these values: the angle, the maximum output voltage, the minimum output voltage, average output voltage, the peak diode current, and the peak capacitor current. Now let's run Pspice. Let's also put a voltage probe here in the load resistor, and let's run Pspice. So this is the output voltage waveform. To get the angle, add trace, and select the VAC. Go to plot, axis settings, axis variable, time, xt, the frequency, then 360 for the degree. Okay? We will locate the angle wherein the input voltage waveform and the output voltage waveform intersect. Maximize. Cursor. Using the cursor, we were able to obtain the angle wherein the input and output waveform intersect. There we got a value of 101 degrees. Now let's measure the value of the output peak voltage. Using the cursor, the maximum output voltage is 310.124 volts and the minimum output voltage is 267.571 volts. For the average output voltage, add trace, click AVG, V, R1, 2, cursor on, then let's measure at the end of the waveform. And the average output voltage is 223.664 volts. Now let's measure the peak diode current. Add trace, select ID1, and select the peak diode current by cursor. The peak diode current in the first period is 11.830 amperes. Now let's measure the peak capacitor current. Add trace, IC1, cursor. Using the cursor, the peak capacitor current in the first period is 11.717 amperes. However, in this type of circuit, the capacitor is initially uncharged in the first period. That's why we will later see that the first period values that we got is significantly higher than the steady state values. To get the steady state values, let's go to the schematic, edit simulation profile, and set our runtime time to 50 milliseconds. With 50 milliseconds, we will be able to show 3 periods. Click apply, OK, and run Pspice. Here we were able to show the output waveform in 3 periods. Now let's measure the steady state diode current. Add trace, ID1. Here in the simulation, we can definitely see that the peak diode current in the first period is significantly higher than the peak diode current at steady state. Now let's measure the steady state peak diode current. In the second period, the peak diode current is 10.790 amperes. Now let's measure the peak diode current at the third period. Here in the third period, we also recorded the same peak diode current, 10.790 amperes. So it just means that the steady state values are characterized by waveforms beginning and ending a period at the same values. Now let's measure the steady state peak capacitor current. At trace, IC1. Here the peak capacitor current in the first period is also higher than the steady state peak capacitor current. Let's also measure. Using the cursor, the peak capacitor current in the second period is 10.003 amperes. Now let's measure on the third period. Here in the third period, we also recorded the same peak capacitor current in the second period of 10.003 amperes. So meaning the steady state capacitor current is 10.003 amperes. Here in table number 1, we can observe that the maximum output voltage of 310.124 volts is near to the value of the input AC voltage of 311.127 volts. Since the capacitor is initially uncharged and the circuit is energized at time equals 0, the diode is forward biased as the source becomes positive. With the diode on, the output voltage is the same as the source voltage and the capacitor charges. We can also observe that the peak diode and capacitor current in the first period is significantly higher than the steady state peak diode and capacitor current. Here in table number 2, we will measure the average diode current, the RMS capacitor current, the average power in R1, power dissipated by the source, and the power absorbed by the diode. Table number 2, we will get these following values in the first period. Now let's go to schematic, edit simulation profile, set our run to time to 16.67 milliseconds, click apply, OK, and run Pspice. Now let's get the average diode current in the first period, add trace, AVG, ID1, cursor on, then let's place the cursor at the end of the waveform, and the average diode current is 2.1239A. Now let's get the RMS capacitor current. RMS, IC1, cursor. The RMS capacitor current is 4.2535 amperes. Now let's measure the average power absorbed by the resistor or the load. Base, AVG, WR1. The average power absorbed by the resistor is 269.457 watts. Now let's get the power dissipated by the AC source. Trace, AVG, WVAC, cursor on. And the average power dissipated by the AC source is negative 357.608 watts. Now let's get the power absorbed by the diode. At trace, AVG, WD1, cursor. And the power absorbed by the diode is 3.9197 amperes. For table number 2, these are the results when we restrict the data at the first period. For additional analysis, let's get the same quantities by their steady state values. Let's go to schematic, edit simulation profile, and let's start saving data after the first period or 16.67 milliseconds. Then let's get the steady state value in the second period, set it to 33.34 milliseconds. Click apply, OK. Run Pspice. First, let's get the steady state value for the average diode current at trace, AVG, ID1, cursor. So the average diode current at steady state is 1.154 amperes. Now let's get the RMS capacitor current. RMS, IC1, cursor on. Therefore, the RMS capacitor current at steady state is 2.7677 amperes. Let's get the average power absorbed by the resistor. AVG, WR1, OK. The average power absorbed by the resistor at steady state is 2.77.081 watts. Now let's get the power dissipated by the AC source. Trace, AVG, WVAC. Here, the power dissipated by the AC source is negative 279.067 watts. Lastly, let's get the power absorbed by the diode at steady state. Add trace, AVG, WD1, cursor. Here, we were able to read the power absorbed by the diode of 1.9259 watts. Based from the gathered data, we can clearly see that the values in the first period is definitely higher than the values at steady state, except for the average power absorbed by the resistor values, wherein at steady state, it is 277.081 watts, and at the first period, it was 269.457 watts.